Okay, today we'll take a look on A320 family V2500 engine fan blades, how to identify blade number 1, we will take a look on its construction, and as well how to inspect the inner structure. So let's take a look at it. Those two engines are quite easily recognizable on the A320. The V2500 looks like old turbojet engine, which basically means that it's one single tube and the cold and hot stream is mixing inside of this one tube. And CFM56-5B, on that one you can really see that turbo fan section is separated from the hot section. This is the biggest difference when you look on those two engines from the outside, and as well CFM56 has a larger diameter. And since I'm talking about the fan, on CFM you can find 36 fan blades, and on V2500 we have only 22. And how we can find blade number 1? Well, regarding CFM, I already made video, link to it you will find up here or later on in description below. And now let's take a look on V2500. When you look on the fan of V2500, in front of the blades you can see inlet cone, inlet fairing, and then blades. But if you take a closer look between the fairing and the blades, you can see small strip of the metal, and this small strip of the metal is actually quite huge and important part of the fan. This is called front blade retainer ring. Actually, that holds the blade on position. You can find, of course, balancing weights on it. And if one SB is implemented, the number of the blade number 1, you can find engraved on this thin strip of the metal on the top of it. If this SB is not applied, you need to remove the fairing and then you will find engraved blade number 1. But if you have this SB implemented, you can find very easily fan blade number engraved on this ring, and that way you can easily find it. Now let's take a look on their constructions. These fan blades are made out of titanium alloy, which provides strength, corrosion resistance, and lightweight. And there is another important information which needs to be mentioned, and that is that those blades are hollow, which means that they are empty. Well, empty. Inside you can find a sort of reinforcement in way of honeycomb. This provides stability and resistance to stress. This type of construction brings a lot of benefits, but also we have one small problem, and that is we can't really say what is going on inside of this blade, because there can be delamination, there can be fatigue cracks and many other problems. So how can we identify this sort of problem with a blade before it reaches critical point? Well, we need to use some sort of non-destructive testing, and in this case we'll use method which is called tap test. And no, we're not going to use that. Well, there are sort of tap test procedures where you use special hammer made for those procedures. But today we're going to use different procedure which is called transient acoustic propagation. And that test I would like to show you today. So let's take a look on the apron. So first of all, we need to prepare our equipment, and that means that we need to assemble it. As you can see here, I have a tester and I need to plug it to the probe, and then we need to test our equipment, and for that we're going to use this metallic block with small plastic insert inside. On the edge of this metallic block we can find exact volume which we need to measure with our equipment. So we'll apply a little bit of gel on our probe. That will gonna help better distribution of the sound. Then I'll activate the testing device which will send the sound wave and read the response. After test I'll get measurement displayed, and if it corresponds with the value which is written on the block, the test pass and I can proceed with the testing of the blades, which exactly happened, so we can proceed with the blades. And as a first I need to locate blade number 1, which I already showed you. And luckily the SB, which I've been talking about before, was applied on this front blade return ring. So the blade number 1 is marked, so I don't need to remove the fairing. Okay, once we found our blade number 1, we can find exact spot on the convex airfoil side of the fan blade where we need to put our testing equipment. Of course, we must be sure that the fan blade is clean, so that will not gonna affect our result. And maybe not everybody of you understand what convex airfoil side means, so let me explain. It is curved outer surface on the fan blade aerodynamic profile. This is the part of the blade that faces the high pressure airflow when the fan rotates, typically opposite concave inner side. The convex side plays a crucial role in generating lift and maintaining efficient airflow through the engine. And with this information, we can continue with our test. And once we have everything set, we can proceed, which means that we'll need to apply a little bit of gel on our probe, and we need to find that exact spot which I've been talking about. Then we put the probe against the blade and we will press the test button. Once tester is finished, we'll get value displayed, and this value need to be recorded in the form. This procedure need to be performed, of course, for each and every blade. Okay, now you more or less know how to perform this test and what we are searching for, but I would like to explain a bit more in the detail what is going on during this testing. The probe will release sound wave which will propagate through the structure, dissipate or propagate through the blade material. Then we measure the rate of the changes in acoustic signal amplitude, which is detected by sensor during the test. It reflects how quickly the sound generated by this probe, and this value is indicated in decibels per second. And of course we want to get as lowest number as possible, because lower decibels per second typically indicates smooth propagation of the sound wave through the structure as the energy dissipates predictably. On the other hand, higher decibels per second suggest irregularities in the wave propagation, which often occurs when the sound wave encounters internal defects such as cracks or delaminations. These defects disrupt the wave's natural flow, causing sharper or irregular changes in acoustic amplitude. For easier understanding, you can imagine internal defect as a barrier or reflector for the sound wave, which amplifying the localized acoustic energy over the time. So, which means that higher decibels per second value served as an early indicator of structural issue that could compromise the fan blade's integrity under the stress. Monitoring these values help the maintaining operational safety and prevent potential in-flight failures. So as you can see, this is again one of the examples how, thanks to technology, we can keep aviation one of the most safest possibility for transport. Okay, that was the last blade. Now all what's remaining is to clean all the blades from remaining gel, which I left there. And then of course I need to pack all my equipment. And now all what's remaining is paperwork. This is all about transient acoustic propagation. If you have any questions, please write them down in the comments below. As always, I would like to ask you to not use this as a replacement for your maintenance manual, but always use latest documentation released by manufacturer. That's all from my side. My name is Tomáš, this was Aircraft Maintenance with Zeto, and I'll see you on next video. Bye.